The second part of the talk, construction of special Lagrangian fibrations on log Calabi surfaces. Again, this is a joint work with Tristan Collins and Adam Jacob. So this is outline of the second talk. I will first give the statement of the main theorem, and then I'll give some applications. And then the second half of this talk will be devoted to prove the main theorem. I first explain the model geometry at infinity, and then I'll tell you what is the special Lagrangian ansatz. And then we'll try to prove that if you run a Lagrangian mean curve flow on this special Lagrangian ansatz, one will have it will smooth convergent to special Lagrangians. So this is the main theorem of this talk. So Y is a Fano manifold, namely it has an n-pole anti-canonical divisor. And I will assume that I can find a smooth anti-canonical divisor D. In particular, so by adjunction formula, D is a one-dimensionless Calabi manifolds. If I can find any special Lagrangian inside this Calabi D, and then on the complement, there exists, recall that there exists the so-called Tianyao metric. Make it a Calabi on X. And then we can construct a special Lagrangian submanifold inside X, and its topology is S1 times the original, the topology of L. So this theorem will give a lot of new examples of special Lagrangians in log Calabi manifolds. And so the first applications is the construction of special Lagrangian fibrations. So in dimension 2, one can slightly weaker the assumption Fano, make it some sort of semi-Fano. And then we can prove that there exists a special Lagrangian fibrations. So not as just a single fibration, spatial Lagrangian, but we get a fibration structure. And moreover, with a spatial Lagrangian section. And so assuming the first theorem, and so this application is the idea of the proof is outlined at the end of the first talk. And so I would just mention a few things. So with the piezo surface, by classification of compact complex surfaces, they're either P1 times P1, or the Hirzebruch surface F2, or broad P2 at generic D points, and D can vary from 0 to 8. And this actually solves some conjectures of Yao and Noru. To my knowledge, this is only non-trivial examples of spatial Lagrangian fibrations so far, in the sense that all the existence example before, one always start with something, some geometry with a non-elliptic fibration already, and then do the hypercare rotation. And later again was Collins and Jacob, we have proved the existence of spatial Lagrangian fibrations using similar techniques. to the case of rationality surface, and D is an anti-canonical cycle. And with a joint, and the joint work was Collins, we'll be able to have more examples when D is not smooth, and hopefully they will appear soon. So the second applications is the Torelli theorem for ALH star gravitational instantons. So gravitational instantons, they are non-compact complete hyperkähler for manifolds with L2 curvature tensors. They're introduced by Hawkins for his building blocks of his Euclidean quantum gravity theory. And so the gravitational instantons, based on many earlier people's work, recently Sun and Zhang have a full classification of gravitational instantons by their volume growth and curvature tensor decay. And so they're named as LE, LF, LG, LH, LG star, and LH star. So the first four are known to people due to their volume growth from R4, R cube, R square, and R. And so the first one is known as asymptotically locally Euclidean, and the second one is the abbreviation for asymptotically locally flat, and then G and H are named by induction. Later, I found another two different gravitational instanton. LG star had the same volume growth as LG, but it has a different curvature decay. While LH star, they behave a little bit like LH, but it has volume growth like R to the power 4/3. So the first five have volume curvature tensor decay. Sorry. The first five has curvature faster than projected decay, while the last one has curvature exactly projected decay. And so the treatment of the last case is different from all the others. And using the construction of spatial Lagrangians, Fibrations, with Tristan Collins and Adam Jacob, we prove a Torelli theorem for LH star gravitational instantons, in the sense that the cohomology classes of the hyperkähler triple uniquely determine the gravitational instantons. And so these are some unexpected applications of our construction. So now I will first explain what is the geometry at infinity, known as the Calabi Ansatz. So we start with a projected Calabi-Yau manifolds of dimension n-1. We take a positive line bundle on this Calabi-Yau, denoted by L. So let's show a picture. So I'll have a Calabi-Yau, so D, and now I'm going to take some a line bundle over it. So the total, this is L. And then we're looking at a neighborhood of the zero section. And I'm going to delete the zero section. I'll call it XC. Since that D is a Calabi-Yau, it has a holomorphic volume form. I'll call it capital omega D. And if we take W to be the coordinate of the fiber of the line bundle. And so if we take dW over W, which with the pullback of the holomorphic volume form of D, that gives you a holomorphic top form on XC, where the C stands for Calabi. To write down the Ricci flat metric, we first recall that L as a positive line bundle. And so there exists a Ricci flat metric such that it's in the Kähler, Kähler class, exactly the chain class of this line bundle. And we can choose a Hermitian metric such that its corresponding curvature form is this Ricci flat metric little omega d. And so we get a Hermitian metric on this line bundle. And for every point on XC, I can view it as a element, a section, local section of the line bundle, and we just take its norm of a section with respect to the Hermitian metric. So then this will give you a function on XC. We further take minus log to a certain power, and then we take the DD bar up to some constant. And this gives you a 1-1 form on XC, but actually it's a Kähler form, and actually this is Ricci flat by direct computation. And so overall, it says that this XC here is a Calabi L, where it's a Ricci flat metric little omega c and holomorphic top form capital omega c. So now we'll introduce L0, we call the scale, as given by this quantity. Roughly, you can view it as measured how far it is from the given point to the point you're looking at. So this is a function on XC. And so one can compute the curvature tensor directly, and the curvature tensor has good decay property. However, the injectivity radius is actually degenerate, as in general n is larger or equal to 2, larger or equal to 2, and so the injectivity radius decay. And so this is not the bounded geometry in general. And that will cause some trouble. So now recall that D is a Calabi L. With respect to a Kähler Ricci flat metric and a holomorphic volume form. And so we can talk about the special Lagrangian inside D. Assume that we can find a special Lagrangian inside D. Then we'll choose any real number epsilon. We choose so for every element inside in L, we look at the fiber of the line bundle and look at the circle with radius epsilon respect to this Hermitian metric. And so topologically, you get L times S1. By direct computation, the holomorphic top form of this Calabi model retreat on L epsilon is given by follows. So if L is a special Lagrangian in D, then this part has a constant phase. And so L, so this whole thing has a phase which is constant. And by direct calculation, omega c, the kilophone on the Calabi model, can be written in this way. So since that L epsilon had this property, in particular, that means that the scale is constant. And so the first term contributes to nothing to L epsilon. And so since that L is a spatial Lagrangian in D, in particular Lagrangian, so omega D restriction on L equal to 0. And so the second term also contribute to 0 when it restrict on L epsilon. In other words, from this construction, if L is a spatial Lagrangian, then L epsilon is a spatial Lagrangian in the Calabi model. And moreover, if D has a spatial Lagrangian vibration, then one can lift them to a spatial Lagrangian vibration in the Calabi model. And in particular, in the case of D is an Euclidean curve, we'll get a spatial Lagrangian, or when X and D is a K3 surface, that is the situation we can have spatial Lagrangian vibration. That's what we know so far. And since everything is explicit, one can compute the metric of L epsilon, induced metric on L epsilon. We can compute the second fundamental form. Since L epsilon, there are spatial Lagrangians, so the main curvature vector is 0. And the first eigenvalue of L epsilon will be completely controlled by this first eigenvalue of the Laplacian of L and the epsilon. And so in particular, the geometry is look like this is D, and let's assume that I will just draw like L as like a point, and then one will lift. So this spatial Lagrangian is like this, probably, or like an S1 bundle over L, and when epsilon is getting smaller and smaller, one get like a thinner and thinner, like a sort of like a cylinder. When you're getting closer and closer to, like epsilon goes to 0. So this is like pictorially, how does this L look like? Or L epsilon look like? So here's how Lagrangian main curve flow comes in. So if L is a graded Lagrangian, what it means is that if it's a Lagrangian, then the holomorphic top form ratio on L is the volume form of L times a function of the form EI theta. And where theta a priori is a function from L to S1, and we call it Lagrangian is graded if we can lift this function from L to R. And recall that L will be a spatial Lagrangian if theta is a constant. So in particular, all the spatial Lagrangians are graded. And so in the case of Calabi, the main curvature vector is just given by this gradient of this phase, twisted by the almost complex structure. And the main curvature flow is given by the evolution of this Lagrangian in the direction of main curvature. It is proved by Smolzek that the Lagrangian condition is preserved under the main curve flow in the Calabi case. And so if one can prove the main curve flow is convergent, namely one can have this goes to 0, then we get the main curvature equal to 0. Then by this formula, main curvature equal to 0 tells you the gradient theta equal to 0, that is theta is a constant. And one get a spatial Lagrangian. And so the upshot is if one can prove the smooth convergence of Lagrangian main curve flow, then one will get a spatial Lagrangian. And so here is the idea of Li back to about 10 years ago. So he proved the following lemma. If along the flow, the second fundamental form is bounded above, and the main curvature, the normal main curvature, is also bounded above. And further assume that the first eigenvalue of the Laplacian on the Lagrangian is bounded below, then the L2 norm of the main curvature vector will satisfy this evolution, will have this evolution inequality. So if this delta minus 2 lambda epsilon is positive, then one can see that from calculus that the L2 norm of the main curvature vector will have exponential decay, where this decay rate will depend on this number. And if one has the L2 norm of the main curvature vector, we can go from the L2 to pointwise estimates. And the idea is follows. So if one can have, if in general one has a function, if the integral is less than a small number, if we can exclude that it has a large variation, so that the first derivative is bounded, then we know that the C0 norm of this function will be small. And in general, we need to worry that the volume element is not degenerating. And so we need to prove a general statement, we need to assume that the volume form is not degenerating. And so in general, if we have an L2 norm, here case that it's coming from above, if the L2 norm is small, and if you have certain gradient estimate and non-collapsing of the volume form, then the C0 norm of this curvature, this tensor, will be small. And with more ideas, I will explain below that Li can prove smooth convergence under quite some assumptions. However, this will not be able to apply to a Calabi case. And the main obstruction here is that the geometry is very degenerate. For example, one will see that from the earlier slides that the first eigenvalues is degenerating. The injectivity radius also is degenerating, and the volume form of L is also degenerating. And there are other quantities are degenerating, and so the original argument does not apply. And another difficulty is that when we run the main curve flow, we don't know a priori there exists any special Lagrangian. And so if one star was a special Lagrangian, and then we do an arbitrary perturbation, then it will be easier to prove the smooth convergence. However, we don't know the existence beforehand. And so remedy for this degenerated geometry is that the main curvature vector, the normal main curvature vector decays much faster than the other quantity. And we need a qualitative estimate for all the geometry, all at the same time. So to adapt the argument of Lee, we introduce the following notion. So we say that L is of CK delta prime bounded geometry. If we can find some constant CK delta, positive numbers, such that the scale reached on L has certain control, the second fundamental form is roughly k to the power minus 1, and the norm of the main curvature vector has exponential decay respect to this k, and the first eigenvalue, although it's small, but it's behaved like a k to the power minus 2, and so on. This are the most important quantities, and roughly this gives you a way to qualitatively control the important geometric quantities of L. And so from the earlier calculation, that the Ansatz spatial Lagrangian L epsilon is of CK delta bounded geometry for k equal to minus log epsilon to the power 1 over 2n. And so in other words, when you choose epsilon very small, this k will be extremely big. And so you can again see that the first eigenvalue is degenerating. And here this C is some uniform constant, and delta prime are some universal constant, and this independent of epsilon. And so one have some pointwise estimates. And so Smelzek has the following evolution equation for A, the second fundamental, the norm of second fundamental form. So first two terms will behave if its equality is like a heat equations with some perturbation. And so from the comparison principle, so one can have the following inequalities, and so that the norm of the second fundamental form will at worst increase linearly. And so notice that if you start from recall that if you start from this initial Ansatz spatial Lagrangian, it's CK delta bounded, whereas this second fundamental form is of the scale k to the power minus 1. And so here that means that you can flow t to an end on an interval from 0 to k squared, that this bound is still, this whole thing is still of order k to the power minus 2. K to the power minus 1. And so similarly, one have the following evolution inequality for the norm of H, the main curvature. And again, for the comparison principle, one will have under the main curvature flow, the main curvature known is bounded by its initial value times this exponential increased function. But again, you can see that so you can run the Lagrangian mean curve flow for t until above the size like k squared, then this term will become roughly like a constant, and then the initial value will behave like a exponential minus k squared, like one see here. And so it will still be in the same bounded geometry of this for the same k. And so the first eigenvalue, one can compute it by the Rayleigh quotient. And then the whole calculation just boiled down to how to estimate the norm of the derivative of the Gij respect to time. And one can easily, again, using the comparison principle to have an estimate of the first eigenvalue. So this usually don't vary too much. And so here comes if you put all these estimates together, one will have the following lemma. So if we have a Lagrangian mean curve flow, if the initial value has ck delta prime bounded geometry, then the Lagrangian mean curve flow will exist at least this long until some constant alpha times k squared, where this k squared is what I explained earlier. And moreover, along the main curve flow, it will stay of, oh, there's a missing c here. It will stay c times 1 plus delta and k and delta prime bounded geometry on this interval. And since this k, you can, if you choose is L0, L0, close is further away from to infinity, then this capital K is huge, and that means that if you move this starting Lagrangian is very close to infinity, then you can flow it longer. So the idea of the proof is you look at this number capital T such that this LT, the Lagrangian mean curve flow, exists for time from 0 to capital T, and such that this bounded geometry is preserved. And the idea is that we use the evolution estimates from what we have above, and one will be able to prove that this number T is actually larger than the minimum of capital T and alpha k squared for some alpha. And so in particular, that tells you that this T will be at least larger than the alpha times k squared. So you know that the Lagrangian mean curve flow can exist this long. This is one of the key idea of the proof. And so one actually will have the improved estimates for the second fundamental form. So small z has another evolution inequality for the second fundamental form. And so assume we can have exponential decay of the main curvature. we fit it back here. So for this, you need to the Nabra square of h, one need more work, but it's actually one can still prove that it has exponential decay. But then again, use the comparison principle. Then one can have the derivative of this the norm of the second fundamental form with respect to time. We'll have this order. Essentially, it will have exponential decay. And since that our initial value is of order, the initial value of a norm square has the order of k to the power -2, then after you integrate with respect to time, all this like exponential decay term will just very small when k is large, and so you see that it is still of the same order, but with a possibly different constant. So now with this knowledge, we can have everything for the smooth convergence. And so what we prove is that if LT is a Lagrangian mean curve flow with the starting point of CK delta bounded geometry, and we prove the Lagrangian mean curve flow as smooth convergence, and all the way it has 4C K and delta prime over n plus 2 bounded geometry. In other words, that the main feature means that it doesn't fall far away. Recall that this because this K will control the scale, while the scale is roughly tell you like the distance from the Lagrangian to the given point. And so if this K is in the same scale, then that means that the location of Lagrangian cannot move too far away from the original one. And the idea is follows. Again, we look at the largest possible T such that Lagrangian mean curve flow exists, and with this bounded geometry, the desired bounded geometry. So from the earlier estimate, so recall that lambda 1 is about k to the power -2, and A is about k -1, and the norm of H has exponential decay. So when k is large, one can see that lambda 1 minus A times H is positive. So that tells you that the L2 norm of the main curvature vector has exponential decay when you have these estimates. And then we use that L2 estimate can lead with the smoothing estimate for H. One can have the one will be able to prove that the C0 norm has exponential decays along the Lagrangian mean curve flow. And one has to use the following evolution equation, again from Smolzek. So all the terms involve H. Since now again we mentioned that since the terms with h has exponential decay, by comparison principle, the normal second fundamental form has a rate k to the power -2, and one can have more precise on this constant, and so on. You want to do all the geometric quantities, how they evolved with respect to Lagrangian mean of flow. And altogether, one will show that LT is actually always 3C K and delta prime over n+2 bounded geometry. And so recall that from a few pages away, we say that if one can have something of bounded geometry, one can always, the flow always can persist for a little bit longer by the price that you increase this number slightly larger. So in other words, that we can actually always, if LT is always, this has this bounded geometry along the flow until capital T, but this is still the 3C here. And so one can flow, since we want this the bounded geometry is 4CK delta prime over n+2, one can actually flow a bit longer, and that the length of this interval has a fixed amount, and so we can always flow at surpass T. And that will contradict to the definition of T, and that actually tells you that the Lagrangian mean curve flow actually have smooth convergence, or T equal to infinity. And that finished it. And that will be the end of the talk. Thank you.